Hello and welcome to Office Hours with Bill Jennings at Klamath Community College. Today I'd like to talk a little bit about combinations of functions and composite functions. We'll start off with combinations of functions, and I'll probably throw it in a second video for the composite functions so that we don't get the two confused and make a 30-minute video out of this. So combination of functions is really just a way for us to talk about having this ability to take two functions and do algebra with them, whether it be addition, subtraction, multiplication, or division. So we could say, just by definition on the combination of functions, what we're going to say is that if I have two functions and I want to add them together, I could just say f plus g as functions added together. I'm just going to take f of x and I'm going to add to it g of x by definition. So if I see this notation where the f and the g are in parentheses, these should be in italics, by the way, f plus g coming together, I'm just going to simply say take the function f, take the function g, and add those two things together. They've got to share that variable x. It's very important. Our textbook or textbook type problems, we're not going to throw that curveball at us, but we should check to make sure that we're all working in the same variable. F minus g of x is simply going to be f of x minus g of x, and this minus sign, what we really probably should say is f of x minus g of x, so that I know I'm going to apply that negative sign or the opposite to the entire formula that's going to come out of g of x. Then these two pieces, fg of x, we're going to say that's going to be f of x times g of x. And note that we are just, these two things are run together, and I'm using a closed circle. When we get over here to the composite functions, you're going to notice that there's this looks like a little zero there, and that is going to be our notation that's going to tell us that we're working with composite functions, is this composed with notation that's right there. Then our division, we're going to have f of x divided by g of x. Now this is something you've probably seen maybe in your intermediate algebra courses, but in this college algebra course, we're going to also focus on the domains that go with this, and that's actually going to be a big issue for us coming down. So this is the nuts and bolts of combinations of functions. We'll come back for composite functions in just a little bit, so hang on to that one. We'll come back to this slide for that one. So one of our big concerns on this combination of functions is that our domain is going to become something of high importance. Now let's consider if I have f of x and g of x. Let's focus on the domain for a moment, and then we'll worry about adding the two together. And the key thing on adding and subtracting and multiplying and dividing is not to overthink the question. So if we have an f of x function that is the square root of x plus 9, if I was to put this on a number line and graph my domain, x plus 9, so we would say x plus 9 has to be greater than or equal to 0, which means x has got to be greater than or equal to a negative 9. So I could come out here to a negative 9, and I could say the green line represents the allowable domain for my f function. Now if I took my g function and I said g of x equals the square root of x minus 4, well then we would say that x minus 4 has got to be greater than or equal to 0, so that means that x has got to be greater than or equal to 4. So if I took and said let's give that a red line, somewhere on this number line lives the number 4, and we're going to say then that this represents my g function domain. Now, if I'm going to take one function, and I'm going to take f of x, and I'm going to add to it g of x, this definition is only going to work for the values that work in both functions. So I have to work on the intersection, which is going to be here where these two functions are defined together. So when I talk about taking down here and going f plus g of x, well that's just going to be f of x plus g of x. Let's not overthink that part of it. It's just take x plus 9 square rooted, and let's add the square root of x minus 4. Let's not overthink it. There's nothing here that can combine because they're all living inside the radical sign. It's just a radical plus a radical. But my domain, this combined function is only going to work on the interval 4 to infinity. Now the reason why is because if I was to pick a number out here, let's just try and do f plus g of x of 1, f plus g of x of 1. Well, that would be f of 1 plus g of 1. Well, f of 1 is certainly defined, but g of 1 is not, because that would be a negative number, and so this would be undefined. I'm not capable of doing it. So this combined function only works under this domain. Now these problems become kind of easy because when we start talking about what's the domain of the addition, well, the domain of the subtraction is going to match exactly because, well, it has to be the same. And then multiplication, we're going to be working under the exact same values there. Now, on the division problems, I have one more thing I've got to think about. So this really means f of x divided by g of x, and so I'm worried about an input that works, but I'm also worried about the fact that, hey, g of x better never throw out a 0 or I'm going to be in trouble. So I have one additional little problem here, because if I take g of, I said g and I wrote f, and I was thinking g the whole way. If I said, let's find g of 4, well, g of 4 is going to be the square root of 4 minus 4, which is the square root of 0, which is 0, which is certainly doable from an allowable input, but that 0 would go out here on the denominator, and that's not going to be allowed. So by the fact that I'm not allowing myself to have a 0 output out of the g function, I'm going to switch in this case, not always, but in this case, because that g of x is on the denominator, I'm going to have to switch from being inclusive to not being able to include that 4. Let's go back and clean up some pieces here on this minus part. So this is going to be f of x minus g of x. Well, f of x is the function square root of x plus 9. G is the function square root of x minus 4. Again, this is the end of the problem, and this represents f minus g of x. Now, I think everyone tends to do pretty well in this section, but then at the end, for whatever reason, people want to set this equal to 0 and try and solve it. We're not solving anything here. We're combining two functions. Nobody has said solve for x, and there's nothing to solve for because there's no value over here to solve for. So f times g of x in this case is going to be the square root of x plus 9 times the square root of x minus 4. Now, in the case of the addition and subtraction, I can't combine radicals with addition and subtraction, but with multiplication I could. So we could simplify this up if we wanted to say, well, that's the same thing as x plus 9, x minus 4, because when you have two radicals, you can combine the radicals under multiplication rule, which then is going to produce, we could multiply that out to a trinomial, which is going to be x squared plus 5x minus 36, and that would all live under the radical sign. Let's pay attention to some notation here. It might come back to haunt us. This is the result of fg of x equals the square root of x squared plus 5x minus 36, and that should all live under the radical sign. I guess we have this last one down here to clean up just a little bit. I've got the fg of x. This is going to be the square root of x plus 9, because that represents f of x right there, divided by the square root of x minus 4, so this would be f divided by g of x here. So, and we have in your homework, you'll see you'll see you want to do the combination of the function and then list the domain. We did the domains first. Wouldn't really matter. You could do it first or last. It isn't going to differ which way you do it. And so this is going to be the result of that. Now, our author, I think, gets a little soft here. He allows this as a final answer, but if we've been paying attention to radicals, we should rationalize that denominator. I believe this is an acceptable answer by your book. If not, maybe you want to go the extra mile and you can rationalize that denominator. Let's look at potentially another example just to help us out just a little bit on this. Let's talk about a domain again. So if f of x, if I look at, I like to draw a number line because this domain for the combination of functions has to be where everything works all the time. So if I look at f of x equals 2x, I can say that that domain is the number line. So we could say that's negative infinity to positive infinity. And then if I focus then on g of x, well, negative numbers work, positive numbers work, but there's a hole in the graph at 0 that says, hey, you know what, you can't ever let this guy ever be a 0 if I ever put these two things together. And we can kind of see it coming together. So this is the result of f of x plus g of x. Now just substitute f of x for what it is. So this is 2x, and g of x is just 1 over x. So we could say that f plus g of x equals 2x plus 1 over x. That's it. That's all there is to it. If you want to force it to add them together, you can. For whatever reason, some people like to set this equal to 0 and solve for x. That's not what we're doing. This is your answer right here. You could share a denominator if you wanted to, but this is going to be okay. Now my domain, though, is going to be negative infinity to 0, and I'm going to union it with 0 to infinity. So I'm putting a hole at 0 because combined, the green line, which represents the f of x, could have been anything, but the red interval represented 1 over x, and it can't be a 0, but because I'm combining these two functions, I cannot find f plus g of 0. That would be something that I cannot do. Now this is going to match here. For the addition, the subtraction, and the multiplication, the division, I'm going to have to pay a little bit of attention to. And in this case, it's going to map out to be exactly the same thing, I believe. Subtraction, we would end up with 2x minus 1 over x. One thing I want to pay attention to here is that this minus sign, if this would have had multiple terms, I might want to put parentheses there so I know that that subtraction applies to both. So this is just 2x minus 1 over x. Multiplying these two things together, it's going to be 2x times 1 over x. Now, even though these x's reduce, so those x's would reduce, this is the result of 2x over x, which equals 2. So no matter what you plug in, fg of x is going to be equal to 2. That's going to be the result. Pick an x, any x, you plug it in, it's going to be that. But you still cannot have it equal to 0 because the original two functions you combined was not allowing a 0 in. Even though it looks like you should have that output, the domain restriction still remains because it's two functions being combined. F divided by g of x, so this is going to be 2x divided by 1 over x. Again, if we do the math, and don't leave this as your answer, that will not be acceptable. Complex fractions are not acceptable. So we're going to have 2x divided by 1 over x, which then turns into 2x squared. So we could say that f divided by g of x equals 2x squared. I'm still going to remain with this domain that x cannot be equal to 0. And if you're using interval notation, it's going to look like this. It hasn't changed. And it's going to remain to be that way because this result, even though 0 can be plugged in here, that result comes from that original function that right here, if you plug in a 0 for that, you're not gonna have good luck. So you have to say that cannot be equal to 0, and so we end up with a little interesting situation there. So that gives us an overview of what it is to combine two functions, and I'm going to make another video to talk about composite functions, and you can watch that one to help you out with that. Take care and have a great day.